Hey everybody, Mr. Piercy here, talking about angle pairs today. This is building off of the lesson that we just got finished with, where we learned how to name angles, how to classify angles, and we would have used a little bit of angle addition. And moving on, we're talking about pairs of angles. And what we're really going to be looking at in these pairs of angles is that they're going to have some kind of a characteristic that's unique to them. And the way that I will be checking to see, do you understand what that unique characteristic is obviously we're going to be asking some kind of a question. Maybe it's going to be concept-based, maybe it's going to be algebra-based, where the heart of the question is really at the relationship of the angle pair, but maybe there's going to be a little bit more to it, again with an explanation or some math, something like that. Looking at the definition of the two angle pairs that we see here, we have adjacent angles, and those generally we would say, well, they have to have a common side, but that's the easiest way of explaining it, but there's a little bit more to it. So that, yeah, they do have a common side, but they also have a common vertex and no common interior points. So we see a couple of examples of angle pair or of adjacent angles. Angle 1 and angle 2 look like they are adjacent angles. They're also looking like they form a linear pair. Angle 3 and angle 4 are also going to be adjacent angles. And next we have vertical angles. Vertical angles are basically going to be two angles whose sides form opposite rays. Essentially, they're going to form lines with each other. So like this ray right here of angle 3 and this ray right here of angle 4, those sides form opposite rays. So therefore angle 3 and angle 4 would be opposite angles or vertical angles. The word opposite angles is often very much thrown around when we're talking about, I want a different color. Vertical angles are often very much called opposite angles also, because they're facing opposite directions at the same vertex. So looking at the diagram that we have here, we have a whole bunch of lines and rays intersecting each other at a common point F. And what I want you to try to be able to do is answer the questions, are they true or false? Now, it says explain, but I really should say if it's false, explain why they're false. So that's really what I want an explanation. If something is false, tell me why it's false. If it's true, well, yeah, it's true. So take your time, pause the video, and answer the three questions based off of the idea of what adjacent angles are and vertical angles are. And when you're ready, come on back and I'll show you what my answers are. All right, I'm guessing that you're doing what I'm asking you to do. At least I'm hoping you're doing what I'm asking you to do. And you should have the answers to the three questions here for the angle pairs. Let's take a look at the first one on the right, the one on top. Angle BFD and angle CFD are adjacent angles. Well, let's see. The drum roll. Here, these are false. That is a false statement. These angles do have common interior points. Let me go ahead and illustrate what I'm talking about. So we have angle BFD. Let me do that one here in red, BFD. And excuse me, let me pick another color here for angle CFD. Well, CFD is here. So anything really, let's try greenish here. Really anything in this area would be interior to both of those angles. So anything in that green area would have a common interior point. So therefore they are not adjacent angles. Angle AFB and EFD. We're looking on the left side of the screen now. Angle AFB and EFD are vertical angles. Drum roll, please. This one is false. The rays FB and FE do not form opposite rays, so they cannot be vertical angles. And last one, angle AFE and angle CFD. That, my friends, is a true statement. Those do form opposite rays for the vertices. So before we move on, again, I do want you to think about it for a second. And again, how is this material, how is it applied beyond our classroom? So on opposite angles or vertical angles, however you want to think of them, or adjacent angles, how could they be used outside of the textbook, outside of the classroom of geometry? So pause the video and think about it for a second and come up with a solution. This is a perfect thing for you guys to share in the comment section of the classroom. So pause the video, and when you're ready, come back and I'll show you what I have. All right. Hopefully you come up with something really interesting. I really want to see what you guys are thinking. How can vertical angles and adjacent angles be used outside of class? Well, here's my example. Railroad tracks. You can very clearly see that we do have a set of, oh, you can't really see the green. Let me pick something brighter. Let's try yellow. We do have vertical angles right here. So this might be angle 1 and angle 2. This might be angle 3 and angle 4 that we saw in our diagram. And of course, angle 1 and angle 3 would form adjacent angles. Same thing with 2 and 3. So there is a perfect example of how we could see or utilize vertical angles and adjacent angles somewhere in the real world. Now here, I know it's a little hard to see on the handouts that I provided, this box here where it says concept summary. What this is telling you, it's telling you things that you can conclude. Now I'm going to read a little bit of it here because there's something as a geometry teacher that I really don't like the fact that they're using. There are some relationships you can assume. I really don't like the word assume because that's something I tell kids never to do in geometry. A better word that I think they could have used here would be something like maybe, and let me change colors here because I can't really see what I'm going to write here. Let me pick something a little darker. I would actually say recognize. There are certain relationships you can recognize to be true from a diagram that has no marks or measures. Yes, because we can recognize that certain things in geometry have a relationship about them that can be measured, that can be proven. Previously, we talked about the hierarchy of geometry, where the basis of it are postulates, statements that can be accepted to be true. Well, from there you can have theorems, where a theorem is something that you could accept to be true, but something you might have to have some explanation. And then you have conjectures. Now, our conjectures are supposed to be proven through another type of reasoning called proofs, where we're using some deductive logic. Now, what we'll do, we will be able to recognize, for the sake of our class, the conjectures that we will create. Those will be true. So we can accept that they will be true. Well, we can use theorems and conjectures that can be proven to recognize certain relationships having certain properties. It's not an assumption. It's something that we're using logic to explain. There's no assumptions involved here. Down at the bottom of the screen here, I know it's not on your notes, but I have two types of triangles. You can make assumptions about what types of triangles those are. But the triangle on the left, you might say it's a right triangle. And what students always tell me why they say it's a right triangle is because they say it looks that way. You cannot assume something is something simply because of the way it looks, not in geometry. You have to be able to conclude what it is or what it is not based on information. Maybe it's information that's given to you by the diagram. Maybe it's information that you can conclude based on some relationship you see. But I can't say that the triangle on the right is an isosceles triangle because it looks like it. I can't say the triangle on the left is a right triangle because it looks like it. I have to have something that tells me that. So if I had a right angle box, then I could say yes, it's a right triangle. If I had congruency markings showing two sides of a triangle to be the same, then I could say, then I could conclude, yes, it's isosceles, but I can't say something is because it looks that way. Okay, so keep that in mind as we go forward. Now, what it's asking you to do here with the diagram, what can you conclude from the information that you see here? Now, there's a lot of things that you can conclude, and I'm not even going to try to write them all down, all right? But here is a conclusion that we can make. And I'm not going to try to write these in complete sentences because, like I said, there are going to be a lot of them. I can say angle 3 and angle 4 are a linear pair. That is not even the only conclusion that I can make from the diagram. Just about angle 3 and 4. I could also say they form a linear, or they are adjacent to each other, because that's one of the things that a linear pair means. All right. So what I want you to do now is to try and write down as many things that you can conclude about the diagram. And when you're done, I want you to pause the video. Let me rephrase. I want you to pause the video, write down as many things as you think you can conclude reasonably in the diagram, and when you're done, come back and I'll list a few of them off. Okay, so again, I'm going to just presume that you are actually doing what I'm instructing you to do and pausing the video and doing the things I asked you to do when it's paused. But just looking at the diagram, I can conclude angle 1 and angle 2 are congruent to each other because of the markings that are there showing that they're congruent. I can conclude angle 3 and angle 5 are opposite angles or vertical angles because their sides are opposite rays. I can conclude that angle 1 and angle 2 would form a vertical angle with angle 4. I can also conclude because angle 1 and angle 2 have a certain measurement. Well, no, let me backtrack. I don't want to try to give anything away here. But we could also say that angle 1, angle 2, and angle 3, all three angles are supplementary. I can have more than two angles that would be supplementary. But so there's quite a few things that you could put here. If there's anything I missed, let me know. But I don't think I missed a whole lot. There's a lot of things there. I just didn't want to write them all down. Now here is where you're going to need your protractor. So hopefully you do have the construction tools that we're really going to need for this class. We're not going to use them a whole lot, but we are going to use them from time to time, and here is the first example of when we're going to use it. What I want to do is use the protractor for you guys to be able to draw a conclusion about these angles. So at this point I'm going to go ahead and I want you to pause the video and do what it tells you to do. Measure those angles. And what do you notice about the pairs of vertical angles? All right, so coming back, I'm going to go ahead and do my best to try and measure these guys here. My protractor can be picky sometimes. So I'm going to take my protractor, try to put the center of the protractor on the vertex. I think that works. And rotate the guy here, and what I'm going to do is I'm going to measure angle AEB first. So nope, that's not what I want. There we go. Now we're cooking with gas. And that looks right around, I don't know, 127 degrees is what the compass is or what the protractor is telling me. You see, if I take my pin off of the board, it changed it to 45 degrees, you silly protractor. It's 100, oops, I moved it. About 127 degrees is what it looks like. So now let's measure, I don't want to measure BEC, I want to go ahead and measure CED. Let me go ahead and turn this puppy around and see what we get here. And I think that's right about there. And again, right now the protractor measures 134 degrees, which it clearly does not. 134 degrees, it'd have to be more like here, and it's not. So 127 degrees again. So at least one pair of vertical angles had the same measurement. And if you do the same thing with the other vertical angles, so here I'm measuring what looks like to be about 54 degrees for angle BEC. And if I turn it around, right about there, I think I'm off just a hair here. I think I had 54 on the other one, so right there is 54, there's 55. So, but you can clearly see the relationship of the vertical angles is vertical angles vertical angles are always congruent. Now here, this is actually known as the, oops, I can't spell, not vertical, vertical, you have just discovered your first theorem. We can make a statement saying that vertical angles are always congruent, but we actually had to do some kind of a process to show, yeah, it is. And if you want to, test it. You don't have to have the angles that I provided for you. Take your straight edge, draw any two straight lines that intersect each other, and measure them. C, do the opposite angles. Again, produce the same measurement. And if you're measuring things correctly, they will. And that is the difference between a postulate and a theorem. A statement is that I can accept as a postulate. A statement that I have to explain, I had to explain this. This is a theorem, but that's your very first theorem in geometry. So congratulations. Now, finding the measurements of some angles. Here I have an example, angle KPL, JPL, they're a linear pair, where angle KPL is some expression, 2x plus 24, and JPL is another expression, 4x plus 36. What are the measurements of the angles? Well, these are very similar to what we have done. Let me pick a color besides black. That one's going to get old here. There we go. Draw a diagram of what it should look like. A lot of times in geometry, I always tell kids, hey, if you don't know what it looks like, draw an angle, draw a diagram. So because it's a linear pair, it's going to look something like that, where I have a straight line and the adjacent side is coming, it's looks like that. There we go, linear pair. So KPL, here's KP, and I'll put L up here. And then we have, not L, here's J, JPL. So there's my linear pairs. Now I have no idea if these are what it should look like. I'm just doing what it tells me to do, draw a diagram. So this is 2x plus 24, and this is 4x plus 36. Well, because a linear pair are really supplementary angles, the sum of the two angles that we have here should be 180 degrees. Again, this is kind of a reasonable expectation or a reasonable conclusion that you can draw by me telling you that they are a linear pair. You can understand a linear pair is a pair of supplementary angles that form a straight line. So we're using that connection to say the measurement of angle KPL plus the measurement of angle JPL must have a sum of 180 degrees. And now that, again, just like what we did with segment addition, that's really the end of the geometry. The rest is plugging in the algebra expressions and solving for x and so on. So we'll say here 2x plus 24 plus the other expression, 4x plus 36, equals 180. And again, we'll do this just like any other algebra problem. Combine your like terms on the left side of the equal sign, and then try to move things across the equal sign. So the x's, 2x and 4x, give me a total of 6 x's. 24 and 36, those together give me a 60 to be equal to 180. So now move the 60 over through subtraction. and I get 6x to be equal to 120. Divide both sides by 6, and x in this case is going to be 60. Oh, not 60. Can't math today. 120 divided by 60 is 20. Okay. Now, once I know x is 20, that is not the end of the problem. Now what we need to do is find the measurements of the two angles. So I'll do here, I'll do KPL. We'll do that one in yellow. So the measurement of angle KPL was the 2x plus 24. So substitute, and I'm going to say 2 times 20 plus 24. So 2 times 20 is 40. 40 plus 24 is 64. So the way I drew my angles, it doesn't look like they're correct, but that's okay. It's just trying to give us some kind of a basis to go on, some form of reference to say, oh, hey, they make a straight line. So now let's go ahead and do the other one, JPL. What's the measure of angle JPL? So the measurement of angle JPL, here we're going to say the 4x plus 36. And substitute the 20 again, so 4 times 20 plus 36. Well, 4 and 20, that gives me 80. 80 plus 36 is going to be 116. 116 degrees. And of course, to verify that I did it correct, does 64 and 116 give me 180? They sure do. So that means x has to be 20. I know I got the right answers, and we're ready to move on. Last thing we're going to be talking about, angle bisectors. These things perform pretty much the same way as midpoint of a segment does. The only difference is instead of cutting a segment in half, well, now it's going to cut an angle in half instead. So what we see here, in the example on the left, ray BD is bisecting angle ABC. So that means the measurement of angle ABD must be the same as the measurement of angle CBD. And we can set up and solve an equation for that. So I'm going to say 4x is equal to 3x plus 6. And I can solve for x here. So that way I can find out what's the measure of angle ABC. Well, move the 3x over, and here I'm going to say x is equal to 6. And if x is equal to 6, well, 4 times 6 here gives me 24. And 3 times 4 plus 6 here, 12 and 6. Oh, something doesn't look right. That gives me 18. That doesn't give me 24. Where did I make a mistake? I don't see what I did wrong. Huh. Let's take a look at the next one here. Same idea. The two angles are being bisected by ray BD. Let me pick a different color. Sure, probably somebody's screaming at their computer, you did this wrong, Mr. Piercy. So let me try the next one. Here I'm going to say 5x minus 11 will be equal to 4x plus 1. And so move the 4x over to the left side, and I'll get x minus 11 to be equal to 1. Move the 11 over through addition, and x will be 12. So now let's try this again. 5 times 12 minus 11. Well, 5 times 12 is 60, and 60 minus 11 gives me 49 degrees here. And here I'm going to say 4 times 12 plus 1, and that will be 48 plus 1, which is 49. So that was working. That looks like a good number. So 49 plus 49, that will give you a total of angle BC to be 98 degrees. And that's what we're really looking at there for our answer. And let's take a look at our last one. Let's go to a different color. Here, 8x minus 16 to be equal to 4x plus 20. And move the 4 over from the right side to the left side, and I'm going to get 4x minus 16 to be equal to 20. Move the 16 over through addition. 4x will give me 36. Divide by 4, and x is 9. So now I'm going to say 8 times 9 minus 16. 8 times 9 minus 16 is going to give me 56 degrees, and then I'll say 4 times 9 plus 20, and 36 plus 20 is 56 degrees. So those look like happy numbers to me, and so that means the measurement of angle A, oops, forgot my symbol here, measurement of angle ABC will be 112 degrees. Okay, so I am human, I make mistakes, and sometimes when I make mistakes, I just start from scratch and see what I'm doing wrong. Okay, so again, BD is bisecting it, so I'm going to try this one more time. 4x is equal to 3x plus 6, so yeah, it looks like x is still equal to 6. 12 plus 6 is 18. I don't know. I think maybe there's a problem with that question. I don't know. Maybe I'm making a mistake. If I am, let me know. But essentially, that's really what's happening with the angle bisector. You're saying I'm cutting an angle in half and seeing what it gives you, because you can set each expression equal to itself. So anyway, we're going to go ahead and close out for today. If you have any questions about how we're using the relationships of angles, what a vertical pair is, what a linear pair is, what adjacent angles are, make sure you let me know. If you have any issues associated with the problems, and again, I wouldn't be upset if you told me what I'm doing wrong here. Maybe there's something I just don't see. It happens sometimes. But I just keep coming up with x to be 6, and I'm not getting, maybe I can't read that number. I don't know. But anyway, thanks for watching, guys, and can't wait to keep going. Talk to you later. Until next time.